So today we're going to discuss the question of when we can actually argue that a function has a minimum and a maximum. And we're talking about continuous functions here. And we're going to actually see a generalization of something that was studied in calculus of one variable. So let's recall that if you have a function from a closed interval with values in the real numbers that is continuous, then it has a minimum and a maximum on AP. The truth is that one could give this for much more general sets, but on a for a calculus course, such sets are more than enough. So one could ask, what exactly is the correct generalization for the interval AB? And what one could say here is that this interval has two basic properties that actually allow the function to have a minimum and a maximum. And those properties are that it's bounded, so it doesn't extend too far, and that it contains its own endpoint. Now, for the case of two-dimensional, three-dimensional sets, we'll use the following. We will say that a set in Rn, we can say in general, will be called compact if it is bounded, so it doesn't extend too far. You can also say that a set is bounded is if it's contained in a disk or a sphere or a ball, I should say, centered at the origin, a large one, of course. And it contains its own boundary. In the language of topology, simple topology, I should say, this property here to contain its own boundary is called being closed. Now, in general, it's not an easy matter to define the boundary of any set. But in our case, we're actually in luck because we can argue that the sets that we will be looking at will be what? I mean, you may have some polygons. And what you want to do here is actually, it would be nicer if I sketch this. I'm sorry, it seems that I attempt to erase this, add them much more. Oh, I think we're good now. Sorry about this. So in any case, I was saying that if we want a set to contain its own boundary, let's mark it in this way with a solid boundary. So that could be a compact set, for example, contains its own boundary, a disk in 2 dimensions, always a triangle, even a line segment. That's a set that actually it is its own boundary in some sense, but it's compact. And these are the kinds of sets that will allow us to say that a function defined on such a set actually has a minimum and a maximum. So the analog of the statement in one variable would be the following. Let K be a compact set in Rn. Here, of course, for what we're interested in, Rn is just R2 or R3, but what we're saying is true for pretty much every dimension. If f from K to R is continuous, then it has a minimum and a maximum. And by that we mean a point. It has at least one point where the output is smaller than every other output of this function on K. And it also has a point, a maximum, where the output at that point is greater or equal to any other output of the function on K. So, so this is a case where the minimum and the maximum are guaranteed to exist. And our goal today is to discuss how we're going to find the minimum and the maximum of a function over a compact set. And as usual, we might take a hint from the case of one dimension, case of one variable. So what did we do when we wanted to find the minimum and the maximum of a function over a closed interval? The answer is that we would look for critical points in the interior of the interval, and then we would juxtapose them with the endpoints, and we would evaluate the function at all those points. So at the critical points in the interior and the endpoint. Whatever gave us the largest output would be the maximum, and it could be more than one point. Of course, whatever gave us the smallest output would be the minimum. Here, of course, for this method to work, we need to have a function which is differentiable in the interior, because that will ensure that if you have a minimum or a maximum in the interior, then the derivative is 0. Therefore, the point can be identified by using the vanishing of the derivative being equal to 0. So we will try to apply the same principle in this case. The only possible issue here is that our boundary, so what will be the analog of the endpoints in our case is our boundary. And our boundary consists of infinitely many points. So it's not that simple to make a list. So if let's say we have a set that looks like this, we could try to study the function individually on the boundary, trying to find points where the minimum and the maximum might occur on the boundary. And then also, so hopefully there will be finitely many. We will achieve this by parameterizing the boundary. And this is where our knowledge of parameterization will start being helpful. And then we will find also the critical points in the interior. Hopefully, we will get finitely many points that we will list, and that should give us exactly what we need. So I think that an example will show exactly how this method works. So let's see. So as our example, let's find the minimum and the maximum of the function f of xy is equal to x squared minus 4xy plus y on the triangle, including the interior, with vertices zero, zero, 0, 2, and 1, 0. So here's what our triangle looks like. So we have this point right here. We have this point right here. We have this point right here. And here's our triangle. And of course, as we said, the interior is part of it. So we're going to proceed in 2 steps. So first of all, we plan on finding finitely many points for which we can have extrema on those points. So let's make a table. And on our first step, we will find so step 1, find the critical points in the interior, the critical points of f, of course. And let's try to understand why this makes sense. I mean, if you have a minimum and a maximum, they might occur either on the boundary or in the interior. And that's actually something that we discussed in passing last time. So technically, a set that is its own interior is usually called an open set. This set that we have here is not its own interior, meaning we have the boundary segment. If we had excluded those boundary segments, then we would have an open set. But in any case, the point is that when you have a maximum or a minimum, that would be on the boundary or in the interior. If it is on the boundaries, nobody guarantees that the gradient of the function has to be 0 at that point. And it's not going to be detected through this way. But if it is in the interior, then the gradient will be 0. So let's find the partial derivatives for f. So the partial derivative with respect to x is 2x minus 4y. And the partial derivative with respect to y is equal to minus 4x plus 1. So if we set them equal to 0, then the second equation gives us x is equal to 1/4. That's the only possibility. And if we plug it into the first equation, then we will get 2 times 1/4 minus 4y is equal to 0, which will mean that y is equal to 1/8. And so from this, we obtain the point 1/4 and 1/8. We're not going to try to classify this point the way we did before, because we're not interested in finding a local extremum. Even though if we found that there is a local extremum at this point, then that might enable us to argue that maybe this point is an extremum. But the word maybe here is the important one. We still wouldn't be able to ascertain that it's an extremum. So what do? Instead, we stop right here and we put this point that we just found on our table. And we say later we're going to evaluate the function on this point and try to compare it to the other candidates. So then the second step, which is the longest step, is to explore the boundary. So how do we explore the boundary here? Well, first of all, to make things convenient for us, let's name the points, the vertices of the triangle. And let's start with finding all points of interest, points where we could have an extremum on the segment AB. Well, the idea here is that we want to go from a function of two variables to a function of one variable. So how do we do that? The idea is to parameterize the segment AB. So this is where our knowledge of parameterizing segments should come in handy, because the segment AB will be parameterized as 1 minus t times 0, 0 plus t times 1, 0, which of course gives us t comma 0. And here t is between 0 and 1. And that's the first time that we use this formula after we mentioned it. And you will see that it will become pretty much our bread and butter when we work with such situations. So now what we're going to do is define the function g of t equals f of r of t, which allows us to find all the outputs of the function f on the segment AB by describing them through one variable. So when we do that, this composite will become, so we will have f of t comma 0, and this composite will become t squared. And here, again, there's a slight abuse of notation, because you might argue, well, why do you plug in a vector into a function that accepts just points? And the idea here is that you start with a vector, you take its coordinates and make a point out of those coordinates, and that's exactly what you're plugging in. But I hope that this intermediate step, which is needed, which is to make the coordinates, to make the vector into just a pair of numbers, is quite transparent and doesn't require much more. So now it's as if you're back to calculus 1 and you have the function t squared, which is defined on the interval 0, 1. Somebody asks you, can you find the points at which this function could have a minimum and a maximum? And now your answer would have been that it could be the points t equals 0 or t equals 1, that's the endpoints. And then for anything else, we need to take the derivative of the function, which is 2t. It won't give us much more, because if we set it equal to 0, we find t equals 0, which is already considered here. So it's the point t equals 0 and t equals 1 at which this function would have a minimum or a maximum. Now we want to put those points back to our table, but we have to be careful. We won't just put 0 and 1. Remember that those are values of the parameter. And through the parameterization, those values correspond to points on the segment AB. What points on the segment AB would those be? I mean, you can plug them back into your parameterization, but it's easy to understand that they're just the endpoints. So what I'm going to put here is 0, 0, and 0, 1. And as we're going to see, in this process, always the vertices that you have on the boundary, like this, if you have a polygon, for example, they will always go into the table. But you might also find other points of interest by just setting the derivative equal to 0. So let's go now to AC. So AC will be parameterized by R of t is equal, so I'm going to use pretty much the same idea, 1 minus t times 0, 0. Does it matter that I put 0, 0 first and not 1, 0? You would have found the same thing. It's just that the segment would be traversed in the opposite way, but it doesn't really matter. Plus t times 0, 2. And at this point, it might be useful to actually mention that what we're using here is maybe the general formula might be useful for everyone. We did it when we discussed parameterization. So if you have a point AB and a point CD, and you want to parameterize this segment, then the parameterization is 1 minus t times the vectorization of the first point plus t times the vectorization of the second point. And here, this will go from 0 to 1 always. That's what I've been using in this consideration. So, of course, I can simplify this, and this will become 0, 2t, and t is between 0 and 1. And again, allow me to call it again g of t. It's not the same g that I had before, but at a different step or sub-step, if you like. And what do we get? Here we will get just 2t if we plug it in. Actually, let me show the whole thing. So it will be again f of r of t, which will be f of 0, 2t. And now if we plug it in, we will get just 2t, because by plugging in 0 for x, the first two terms will become 0. So here you have a linear function. Linear functions do not, with non-zero slope, we do not have critical points. So even if you take the derivative, you will see that it's 2, so you don't have any critical points. The only things that are going to be of interest are the endpoints at t equals 0 and t equals 1. And again, you should try to translate those values of the parameter to points. How? By putting them back into the parameterization. So t equals 0 gives you 0, 0, and t equals 1 gives you 0, 2, which are the two endpoints. 0, 0 has already been included, so we're just going to put 0, 2 on our table, and you will see that now all 3 points are included. Let's go to BC now, which is actually the most useful of these points. So let's see. So we have R of t. As before, it's going to be equal to 1 minus t times, let's start with 1, 0, point on the x-axis, plus t times 0, 2. And this can be rewritten as 1 minus t, comma 2t, and t will be, as usual, between 0 and 1. So now we again want to take g of t, which is f of r of t, and this will be f of 1 minus t, comma 2t. Here's where we're going to get something much more interesting. So plug them into your formula. Let's show now the whole thing. It's going to be 1 minus t squared minus 4 times 1 minus t times t, right? So wherever I see an x, I put 1 minus t. Wherever I see a y, I put actually 2t plus 2t. Let's work this out a little. So this will be 1 minus 2t plus t squared minus 8t plus 8t squared plus 2t. Okay, how does that simplify? So we have 9t squared minus 2t plus 2t cancel each other, minus 8t plus 1. Okay, so we need to take the derivative, and the derivative will give us 18t minus 8. If we set it equal to 0, we'll get t is equal to 8 over 18, which can simplify to 4 over 9. And as soon as we get this, we should ask ourselves, does the point 4 over 9 belong to the domain of definition of this function that we're working with, which is 0, 1? And the answer is yes. So we should still consider the endpoints, but in this case, the endpoints will correspond to what? To just the endpoints of this segment that are already on our table. So this corresponds to 1, 0. This corresponds to 0, 2. This is the only one interesting one. What does it correspond to? So you will have 1 minus t, that's 5 over 9. And then you will have 4 over 9, which is 2 times 4 over 9, which is 8 over 9. So that's a point that we found that is something that we would like to add to our table. And now our table is complete, and we have 5 possible 5 candidates for our extrema. So what we want to do is evaluate the function on each one of them. Since these are the only candidates for extrema, whatever turns out to be the one with the largest output will be the maximum. Again, you may have it at more than one places, and whatever turns out to have the smallest output will be the minimum. So let's try to do the computation. So we have, if we plug in 1/4 and 1/8, we will have 1 over 16th minus 4 times 1/4 is 1, so minus 1 over 8 plus 1 over 8. So here these two things cancel each other, and the output is simply 1 over 16. Plugging in 0, 0 is very simple, so that gives us 0. Plugging in 0, 1 is again pretty simple, it gives you 1. Plugging in here, I wrote, actually, it was not 0, 1 that I should have written here. It was 1, 0 I should have written. And 1, 0 will give us again 1. So we're in good shape. And 0, 2, if we plug in 0, 2, we're going to get simply 2. And finally, that should be a little more interesting. Let's plug in 5 over 9, so, and 8 over 9. So this will give us 25 over 81 as x squared. And then we will have minus 4 times 5, so 20 times 8 is 160, so minus 160 over 81. And we will also have plus 8 over 9. And we might as well set it up with a denominator 81, so that's 72 over 81. And that will give us what? So we have minus 160 plus 72 is 80, minus 88. And minus 88 plus 25, that's going to be minus 63. So minus 63 over 81. What really matters is that this is a negative number, exactly because everything else has been a positive number. That is going to give us our minimum. So as a conclusion, this is going to be the minimum, and this is going to be the maximum. And that's it. So let's recap. What did we do here? We started with our function of two variables, and we said that the minimum and the maximum can occur either at a critical point in the interior or at some point on the boundary. And as far as the boundary is concerned, we can be a little more precise. Upon a parameterization of the specific components of the boundary, it would be a point of the boundary where that parameterization, when plugged into our function, will produce either a critical point or it will be an endpoint of the parameterization. So that pretty much gave us the endpoints of each boundary component. And then in the first two cases of A, B, and AC, we were not able to find any critical points in the interior of the parameterization. In the last case, we did find such a point. That corresponding to a point in the interior of the segment BC. We put that in our table, and our table was complete with all the possibilities. We took those points, we plugged them into our function, and we saw what came out to be the largest and smallest. And that gave us our minimum and our maximum. And this completes today's lecture. Thank you so much for watching.